An exchange of energy between the system and its surroundings but not exchange of matter. So what's something that, like, thermal energy can be exchanged with it, but never matter can go in or out? Pardon?
An engine?
An engine, okay. But there's like gas going into an engine, right? Like there's things, yeah, go ahead. A what? A candle? But it's releasing CO2, which is a type of matter. What if we had, say, like a bowl of soup with a lid on top? Or just say a bowl of soup. The energy can come off of the bowl of soup, right? Matter can be too.
But isn't it exchanging like H2O? Like
Yeah, I guess so if it's releasing steam. That's a good point. Okay, let's leave the example for a minute. I'll think
Maybe
of
it's
a
a
better.
bowl of cold soup. It's not really releasing ice.
Let's leave the example for a minute. I'll think of a better one. Okay. I got a good one for open systems though. That's way easier.
Are these like systems when you're doing a reaction?
Yeah, like how do you keep? Yeah. Anyways, I'll get a better example for you. So now let's think for an open system. This is an exchange of both.
Open systems.
Yeah, I know. I didn't give a space. Sorry. Both energy and matter between system and surroundings. So that example, that's like a lot of things. So say like a flower in a pot. So you add water to the flower pot, so that's like matter, you're adding water. It's releasing oxygen, it's taking in carbon dioxide. It can exchange thermal energy. So there's like matter being put into the pot, like the water, and matter can come out of the pot too. Now an isolated system, what do you think is an isolated system then?
One with no surroundings.
Oh, well, it has surroundings, but it can exchange either matter or energy. Yeah.
Put another one for open that, but the engine will be an open system.
Yeah, a lot, like mostly anything will be open. You want to think of another example?
No,
So say, let's go with our bowl of soup example. We can have a bowl of soup and we can eat it, or we can put a little bit of extra salt in it, or something. So we can add matter, we can take it away, and we can like blow it, get it cooler, you know, we could heat it up in the microwave, we can add energy, you know, okay? Now an isolated system is exchange of neither energy or matter between system and surrounding. So if we're thinking of like, you know, probably like there's nothing that is perfect and can't like will seal in all of its thermal energy or won't let any other thermal energy out. but kind of a theoretical example would be like a thermos. You know, some thermoses that are like really, really good quality, you know, you can put in your hot liquid and it will stay really hot for, you know, maybe like 7 hours. But if you left it for probably a year, it probably wouldn't be as hot as when you put it in, right? And it, well, if there was any milk added, yes, then it would be not good. So there will be some sort of die-off, but for most like really high quality thermoses, you know, you could go ice fishing and in the morning you put in your hot coffee and it could still be nice and warm for you 10 hours later, you know? Yeah. That would be a good thermos. So we have to keep this in mind when we're talking about chemical reactions because whatever we have at the beginning of the reaction, you know, and what we have at the end had to have come from somewhere. So we can't get stuff at the end and the other stuff just float away. Like the reactants and products have to balance out. And this is explained in the law of conservation of mass. So this is an important law for you to know. If, say, on a test, I gave you a multiple choice question and you had to figure out which one was the law of conservation of mass, that's what I'd probably do. But you won't have to, like, write it out. Okay, so let's read it together. This law states that during a chemical reaction, the total mass of the reactants is always equal to the total mass of the products. So basically, we have the mass of the reactants needs to equal the mass of the products. We can't just have the reactants disappear into nothing. Or what if we get more? What if there's more mass of the products than what you start with? Well, it's almost like you had to have something almost from the air that was added to it. And there are reactions that do that. What's the one that I do in Chem 20? Where if I burn magnesium, so an example of this, if I get more, oopsies. So say I take magnesium, it's a reactant, and I burn it. And I end up with a product, so I get ashes, right? Remember I burned magnesium for you that one day, some of you? I think the volleyball players were gone or something. We can maybe do it again. But if we take the mass of the magnesium and the mass of the ashes after, this will be more. So this will be heavier. Why?
So the ashes are heavier?
Yeah. Well, that doesn't make sense according to this law, right? Like if I weighed the magnesium before and then I weighed the ashes after, how could the ashes weigh more if this law says that they can't, person?
When it burns, would it take in some like surrounding gases and stuff like that?
Exactly. What type of gas do you think that it would want to take in? When we burn something, it takes in oxygen. So what actually happens is we add oxygen to magnesium when we burn it, and then we get magnesium oxide. So that's kind of interesting because like when we weigh it at the beginning, the magnesium is just a strip of metal. We can't weigh the amount of oxygen that was added, right? Because it's just in the atmosphere around us. So we don't, it's like we didn't take it into account. But then when we weighed the ashes after, it had changed because it was magnesium oxide. And magnesium and oxygen are heavier than just magnesium. Okay?
Is it MgO2?
No, because magnesium is Mg2 plus and oxygen is O2 minus, so then when you crisscross, it's just MgO. And it ends up as a solid. Do you want to do that?
Yeah.
Yeah. Let's see. I'll show you. We are gonna